A rocket's ability to escape Earth's atmosphere boils down to the principles of thermodynamics, Newton's laws of motion, and the engineering behind its propulsion system. Here's how it works: rocket propulsion and Newton's third law. Rockets operate on the principle of action and reaction. Inside the rocket engine, fuel, usually a mix of a liquid or solid propellant, like liquid oxygen and hydrogen, is burned in a combustion chamber. This combustion produces hot, high-pressure gases that are expelled at tremendous speed through a nozzle at the back of the rocket. According to Newton's third law, for every action, there's an equal and opposite reaction. The rocket is thrust forward as these gases shoot backward. This thrust is what powers the rocket upward. Overcoming gravity, Earth's gravitational pull is strongest near the surface and weakens with altitude. To leave the atmosphere, a rocket must generate enough thrust to overcome this gravitational force. The key metric here is escape velocity, which is the speed a rocket needs to reach to break free of Earth's gravity entirely, about 11.2 kilometers per second, around 40,320 kilometers per hour or 25,000 miles per hour. However, to simply exit the atmosphere, about 100 kilometers above Earth, known as the Kármán line, it doesn't need to hit escape velocity yet, it just needs sufficient upward momentum. Thermodynamics and energy conversion. The burning of rocket fuel is a thermodynamic process. The chemical energy stored in the fuel is converted into thermal energy during combustion, and then into kinetic energy as the exhaust gases are accelerated out of the nozzle. Modern rockets are designed to maximize this energy conversion efficiency, ensuring they produce the massive thrust required to lift their own weight, payload, and fuel against gravity. Staging for efficiency. Most rockets use a multi-stage design. The initial stage has large engines and fuel tanks to lift off from the ground and push through the dense lower atmosphere. Once that fuel is burned, the empty stage is discarded, reducing the rocket's mass. Subsequent stages, with smaller engines, take over to push the lighter rocket higher and faster. This shedding of weight allows the rocket to accelerate more effectively as it climbs. Atmospheric drag and design. The atmosphere creates resistance, drag, that slows the rocket down, especially in the lower, denser layers. Rocket designs are sleek and aerodynamic to minimize this drag. As the rocket ascends, the air thins out, reducing drag and allowing it to gain speed more easily. By the time it reaches the upper atmosphere, the resistance is negligible, and it can coast into space. Achieving orbit or beyond. Once out of the atmosphere, the rocket doesn't just stop, it either enters orbit, by achieving a stable horizontal velocity that balances gravity's pull, or continues accelerating to escape Earth's gravity entirely, depending on its mission. For example, satellites need orbital velocity, around 7.8 kilometers per second, while missions to the Moon or beyond aim for escape velocity. In short, a rocket escapes Earth's atmosphere because its powerful engines convert fuel into high-speed exhaust, generating enough thrust to overcome gravity and atmospheric drag. Clever engineering, like staging, ensures it can keep accelerating as it climbs. It's a perfect blend of physics and human ingenuity.